All right, complex zeros and the discriminant. So recall from the last unit, normally we try to factor a quadratic equation, and that's how we'd solve it. We could also complete the square. We could graph it if we just wanted to estimate. But when you cannot factor it, there's nothing else left to do. You use this big quadratic formula, which I have here down in the little chart below. But a way to analyze it is if you look at the number underneath the radical. So I'm talking about this little piece right here. If you analyze that b squared minus 4ac, there is a way to know whether or not it's going to have real solutions or imaginary solutions kind of ahead of time. So we're going to just really quickly do one with the quadratic formula just to get back familiar with it and sketch a quick graph, and then we will actually do a little bit more work with just the discriminant part. So that's what this little phrase, discriminant, it just refers to what's under the radical. So just the b squared minus 4ac piece. All right, so let's go ahead and let's kind of do this first example. It says find the zeros. So remember, zeros are where we cross the x-axis on a graph. But basically, I'm trying to figure out when are the y values going to be 0? What x's make this y value 0? Well, normally I'd try to factor it, and I cannot find two numbers that multiply together to make 7 and add together to make -5. So I'm like, oh, this is nasty. I could either complete the square or use quadratic formula, and we're going to use the formula. So a is the coefficient in front of the x squared, b is in front of the x, and c is the constant at the end. So there's my a, b, and c. And let's run it. Quadratic formula is the opposite of b, or negative b, plus or minus b squared minus 4ac. And I'm going to do this in blue just so you kind of get used to seeing it. So b squared subtract 4 times a times c. And all over 2 times a, which is 2. And we kind of run this thing and we get 5 plus or minus the square root of, well, that's 25 minus 28. So that ends up being a -3. And we're going to find out here in a second. Right at this point, I know that this thing is going to have imaginary solutions. It's going to have 2 imaginary solutions, meaning that it never crosses the x-axis. There is no place where y actually does equal 0. And how we kind of clean this up is, remember with imaginary numbers, we kind of said, well, hey, if we have the square root of -3, that's really the same thing as the square root of 3 times the square root of -1. And then we invented these imaginary numbers, I, that you can substitute in for the square root of -1. So I'm going to just replace that down here. And so I'd say, okay, 5 plus or minus the square root of 3i all over 2. And these are my 2 solutions. Now, if I were to graph this part, if I were to kind of graph, and I'm not going to sketch it on this graph, but I'll just kind of show you using GeoGebra. Might be a little quicker than pulling up the calculator. But I'm going to pull up GeoGebra. Not GeoGebra, Desmos, sorry. Pull up Desmos. And we are graphing y equals x squared minus 5x plus 7. And look what happens. It kind of comes down, it crosses right here at 7, and then it has its lowest point right there. It looks like at about 2.5. And then it comes back up, but y value is never 0. So it doesn't have any real roots. So you could sketch that little graph there in the notes. I'm going to kind of just leave it blank, and you guys could put that in your graphing calculator and kind of sketch it yourself. But it never crosses, so I think it just kind of, it came down somewhere. Just kind of give a little quick and dirty sketch. Kind of did something like that. So when it's floating above the x-axis there, we know that we have no real zeros. All right? And that automatically means we're going to have 2 imaginary roots. All right? So kind of coming down. So the expression underneath that radical is called the discriminant, and it can be used to find the type and the number of solutions to a quadratic equation. Always make sure, this is pretty important right here, always make sure that it's in standard form, meaning that you have the x squared term, the x term, and the constant all on one side and 0 on the other. So if you notice, like this one and this one are not in standard form. All right, neither one of those two are. This one's okay. This one is in standard form. So kind of looking at our chart, here's what happens. If that discriminant is a positive number, all right, so if the discriminant is positive, you are going to get two distinct, two separate real solutions. Now, if what's inside that radical ends up being 0, then your radical kind of just disappears, and you end up with a double root. And it doesn't necessarily have to happen right there at 0. It could be over here. It kind of bounce up. But you're only going to have one place where y equals 0, as opposed to 2. And then if you get a negative number under there, that's when we get two not reals, or two imaginary. And we'll talk about complex here in a second. So you can either have 2 real, 1 real, or 2 not real, or aka imaginary. So a big part of the practice today is finding the type and number of solutions. So you just look at the equation. You don't have to solve the whole thing. We just want to know ahead of time, hey, what type of zeros do we have? So looking at this first one, I need to check b squared minus 4ac, and I got to see, is it positive, negative, or 0? So let's do b squared, which would be negative 4 squared, take away 4 times a times c. Well, this comes out to be 16, take away 16. So this equals 0. So I know that this is going to have one real root, or one real 0. And if I were to graph that, I could verify that it's going to come down and just touch the x-axis. I'm not going to do that here, but you could. Now this one I need to rewrite, and I need to get it in standard form. So I'm going to go x squared minus 4x. I'm going to move that negative 8 to the left side and call it positive 8. So technically I added 8 and I added 8. So now it's looking a little bit better. So now I'm going to do my discriminant. I'm going to say, okay, b squared minus 4 times a times c, and I get positive 16, take away 32, which is negative 16. All right, so since I'm negative 16, that means I'm going to have two imaginary zeros, or non-real, depending on the vocabulary you want to use, two non-real zeros. So he's going to be a floater. I know that one's going to be a parabola floating above the x-axis. It'll be kind of this scenario right over here. All right, next one, let's get this in standard form. X squared, we're going to move the 4x over. The negative 2 is okay. Call that 0. So here we have b squared minus 4 times a times c. So that's 16. And then negative 4 times 1 times negative 2, well, that's a plus 8. So that comes out to be 24. So since it's positive, we know that this one is going to have two real solutions. It's going to come across and cut through the x-axis twice. So it's going to look something similar to that. At least we know that it crosses two different places. All right, so we're just using the discriminant to get a little bit of information ahead of time. Now recall from the quadratic unit that when you take the square root of a negative number, you end up with an imaginary number. I just showed that on the page before. So again, like if you had something like square root of negative 4, well, that's just the square root of 4 times square root of negative 1, which would just be 2i. All right? So that's an imaginary number. Well, a complex number, we didn't really talk about these. A complex number is a number that has a real part, all right? So it has this real piece, but then it also has an imaginary part, you know, an I component there. So an example of that might be something like, you know, 4 plus 2i. That's called a complex number because you have the imaginary part and you have the real part. And it could be reversed. It could be like 7i minus 9. All right, that's still a complex number. Typically, they're going to put the real part first. So I'd want to move the negative 9 to the front and put the imaginary to the back. So this is the exact same thing as this, just kind of written in a more traditional form. So let's move on to number 2. I want you to kind of see this in action. So it says, find the zeros of the function x squared minus 2x plus 5. So I want to find the zeros. And can't think of two numbers that times together to make 5, add together to make negative 2. So quadratic formula is about to come into play. So we have negative b plus or minus the square root of, here comes the discriminant, b squared minus 4 times a times c, all over, I think I should put that in blue, all over 2 times a. All right, cleaning that up, we get 2 plus or minus the square root of, well, that is 4 minus 20, which is a negative 16, all over 2. And when I clean that up a little bit further, I'm going to get 2 plus or minus, and square root of 16 is 4. And the negative, I'm just going to fix that by putting an I there. And I'm just going to divide it all by 2. So I'm just kind of simplifying as we go. And now remember, I break this up. 2 divided by 2 plus 4 i's divided by 2. Kind of separate it. And really, I get 1 plus 2i. All right? Or 1 plus or minus. I'm sorry. So these are my two. These are my two. It looks like just one, but there's two solutions. You know, really, I have 1 plus 2i and 1 minus 2i. Now, whenever you have imaginary numbers like that, and you do the quadratic formula, they're always going to come in pairs. All right? You're always going to have both of these. Oftentimes, we write it all in one expression, but there's really two pieces. Now, those two pieces have a special name, and the two solutions are called complex conjugates. Probably haven't heard that term before, but complex conjugates have real parts that are equal. So this is the real piece that's the same. And then they have opposite imaginary parts. All right? So your front number is the same, but your back numbers, one's positive, one's negative. You get into this a little bit more in pre-calc, but the big thing is knowing that they come in pairs. You're never just going to have one of them. They always come in pairs, and you should be able to find the conjugate if you're given one of them. So for instance, if I have 2i minus 8, first thing I want to do is I want to rewrite it normally. So I'm going to do the real part, and I'm going to do the imaginary part. All right, so just kind of up above, I'm just going to write, this is real, this is imaginary. And if that's one of the two, then his partner, all right, his conjugate is going to be keep the real part the same, but change the imaginary piece. So there's the partner to the one up above. All right, this one's a little easier. If it's 7 plus I, the conjugate is just 7 minus I. Now this one, if I have negative 4i, well, how you kind of have to visualize it is the real part's really 0. So I have 0 minus the imaginary part. So 0 plus 4i is going to be the conjugate, which, since we're adding 0, it's really just 4i. So you might kind of see a shortcut and be like, well, if it's negative 4i, I just got to change it, since it's just the imaginary part. This top one, since it's plus, I'm going to do the real part plus the imaginary part. So the conjugate is going to be the same real, opposite imaginary. All right. So that's pretty much the skill that I need you to have today is be able to check the discriminant, know the number and the type of solutions, And then if I give you one of the two conjugates, know that you can find the opposite one. All right. Quick little set of notes, but hopefully it helps you out on the practice. See you.